Hi everyone! Today in this video we are reviewing intermolecular forces. So we did talk about hydrogen bonding a little bit previously in this chapter, but now we're going to go into a little more detail. So if you felt a little rusty earlier on intermolecular forces, hopefully this lecture will help with that. So let's start with London dispersion forces, or these are also known as van der Waals forces. This is the weakest force out of the intermolecular forces. And really, London dispersion forces occur when you have an instantaneous dipole moment. So for instance, let's say we have a helium atom. And how many electrons does helium have? 2. Okay, so we could draw 2 electrons kind of floating around this atom. But what happens if the electrons are floating around and for a very brief moment in time, they're both on the same side of the atom? Well, we end up with a partial negative charge on one side of the atom and a partial positive charge on the other side of the atom. And this creates a dipole moment, but it's instantaneous. So this could change in a second or a fraction of a second. Now, let's say there's another helium atom that's nearby. If one helium atom has an instantaneous dipole moment, that could cause another nearby atom to have its own instantaneous dipole moment. So the partial negative charge on our first helium atom, the negative charge could repel the electrons in the nearby helium atom. So now that helium atom also has an instantaneous dipole, and the partial negative is attracted to the partial positive. So now those two atoms are attracted to each other. They are feeling a force between them, but it's a really weak force because, again, this could change in an instant. All right, so this force is, again, a weak but stabilizing interaction. And the more surface area you have, the greater the force. More surface area equals greater force. And that's actually going to increase the boiling point of the element or the molecule, depending on what you're looking at. So maybe instead of helium atoms, we look at argon atoms. Argon is another noble gas, but it has way more electrons and it's much larger. So with a greater surface area, argon would have a larger boiling point than helium. Now, another example, I'm just going to erase these helium atoms, make some space here. What if we compare 3 different molecules that do not have a dipole moment? So the only force that they feel are dispersion forces. So let's compare pentane, which is a molecule that has 5 carbons in a row, and then all of those carbons are also bonded to a certain number of hydrogens. Now previously we said that carbon-hydrogen bonds are nonpolar, So this whole molecule is nonpolar. And then let's also look at a molecule called 2-methyl butane. So this molecule also has 5 carbons, but they're arranged a little bit differently. So there's going to be some branching. So we have 3 carbons there, and then I'm just going to write CH3 for these 2 carbons kind of coming off of the end. So each of those carbons that are branched out, they have 3 hydrogens attached to them. But just to save space, I'm going to write it that way. Okay, so 2-methylbutane has a branched carbon, so there's a branch of carbon coming off. Okay, and then let's look at a molecule. Let's see if I can squeeze it in here. Oops. You can see we're going to talk about geckos next. So this molecule is 2,2-dimethylpropane. And again, we'll learn how to name these molecules later on, but don't worry about it for now. So in this molecule, we have a central carbon, and then it's attached to 4 methyl groups. Or 4 CH3 groups. Okay, so we already said that if something has more surface area, it will have more dispersion forces and therefore an increased boiling point. So which of these molecules do you think will have the greatest boiling point? Or another way to ask this is, which molecule has the greatest surface area? Pentane, right? Pentane is this long chain of carbons with hydrogens attached. So that would be the molecule with the most surface area. So it should have the highest boiling point. And in fact, its boiling point is 36 degrees Celsius. Now, which of these molecules do you think would have the smallest boiling point or the lowest boiling point? 2,2-dimethylpropane. So the last molecule on the right, that is going to have the least surface area. Everything's really compact. Everything's centered around that carbon in the middle. And its boiling point is in fact 10 degrees Celsius, so much lower than pentane's boiling point. Now, 2-methylbutane's kind of in the middle. Its surface area is lower than the surface area of pentane, but it is greater than the surface area of 2,2-dimethylpropane. And its boiling point is in the middle at 28 degrees Celsius. So this is just something to think about. If you're comparing molecules that are all nonpolar, the molecule with the most surface area will have the highest boiling point, and then the molecule with the lowest surface area will have the smallest boiling point. Okay, so let's talk about geckos. So one interesting thing that your textbook brings up are that geckos actually can crawl up walls due to dispersion forces. So even though we just said that dispersion forces are the weakest force, if you have a bunch of dispersion forces, so a large surface area of dispersion forces, then you can really do some amazing things like crawl up a wall. So if we zoom in on one of these pads on the gecko's foot, you can see that there are tiny little microscopic hairs. And there's a bunch of these hairs. Now, each of those hairs can stick to a wall just based on dispersion forces. So that's one really cool thing about geckos. So more surface area, again, equals greater force. And scientists are actually trying to utilize this concept in different ways. So practically, they're coming up with band-aids that will have greater attraction to our skin. They're also doing some fun stuff like trying to come up with devices that'll allow humans to crawl up buildings, etc. All right. So now let's talk about the next intermolecular force, which is the dipole-dipole interaction. So this force is stronger than London dispersion forces. So this is actually dependent on dipole moments. So as an example, let's look at a molecule that has a dipole moment. So this molecule has some carbon-carbon bonds, which are nonpolar. It has some carbon-hydrogen bonds, which are also nonpolar, but it has a carbon-oxygen bond, which is polar. And we saw that in our previous video. So this molecule has a dipole moment where electrons are moving in one direction towards the oxygen. Now, let's say we have another molecule that's exactly the same as this one. Now, naturally, the other molecule is going to orient itself so that the electron poor region, or the partially positive region, will be attracted to the negative region of the other molecule. All right, so we can see that the positive end of that molecule on the right is attracted to the negative end, or the electron-rich end, of the molecule on the left. So let's kind of summarize that and write that down. So the electron-rich region of one molecule is attracted to the electron-poor region of the other molecule. Now, again, this is also a stabilizing interaction. Also, I'm not sure why my pen decided to write in bold for a few words. I might need to change out the tip of my pen. Okay. Now, our last intermolecular force is hydrogen bonding, which we did talk about previously. So, hydrogen bonding is one of the stronger intermolecular forces. And out of the three we've covered so far, hydrogen bonding is the strongest. So this is stronger than dipole-dipole, although hydrogen bonding is a type of dipole-dipole interaction. It's just stronger than your typical dipole-dipole interaction. So with hydrogen bonding, we are looking at hydrogen in particular. But that hydrogen has to be bonded to either fluorine, oxygen, or nitrogen. And remember, you can remember this using hold the phone, F-O-N. All right. Now, the other part of this is a hydrogen atom might be between its bonded electronegative atom and a lone pair on another atom that's also electronegative. So let's look at water as an example. This is probably the best example. So water will, well, here, let me draw this first. Sometimes it's hard to draw and talk at the same time. So water looks like this, although I'm going to fix my bond here. Got a little weird. Okay, so water molecules do have a dipole moment. Oxygen-hydrogen bonds, as we've seen before, are polar covalent. So if we draw our dipole moments, we can see electrons are mostly moving towards oxygen. So that tells us that oxygen is electron rich and the hydrogens are electron poor. So you could also write those partial negative and partial positive signs. Now, let's look at this hydrogen here that's in between the two water molecules. Or, well, it's attached to one, but it's near the other one. So that hydrogen is attached to a very electronegative atom, oxygen, but it's also near a lone pair on the oxygen of another water molecule. And that is going to create our hydrogen bond. Now, that other atom that the hydrogen is attracted to has to be fluorine, oxygen, or nitrogen. It can't be just any old electronegative atom. So for instance, let's say we had HCl next to a water molecule. Now, the hydrogen that's in the middle there, it might be attracted to that chlorine because of the dipole-dipole moments. However, it's not going to form a hydrogen bond. It's only going to form a dipole-dipole interaction because chlorine is not one of our very electronegative atoms, fluorine, oxygen, or nitrogen. So that's just something to keep in mind. Hydrogen bonds only occur between hydrogen and fluorine, oxygen, or nitrogen. Okay, so let's just summarize that, and I'm actually going to erase this bottom part here. So the electron-poor hydrogen is attracted to the electron-rich oxygen. And this is a very strong interaction. Okay, so let's summarize all of our different forces. So we started with London dispersion, also called van der Waals. And then we talked about dipole-dipole interactions. And then H bonding. And there's actually one more intermolecular force, ionic bonding. So ionic bonding is actually stronger than hydrogen bonding by quite a bit. So if we draw an arrow here, we're going from the weakest force up to the strongest force. So this would be our order of strength. So water does experience hydrogen bonding, but something to keep in mind is that even if you have hydrogen bonding or let's say dipole-dipole interactions, everything has London dispersion forces. So even water has or experiences 25% dispersion forces. So 25% of the interactions in water are due to London dispersion forces. So everything experiences dispersion forces, but typically we talk about the strongest force that a molecule experiences. All right, so let's look at some examples. So let's consider CF4 carbon tetrafluoride and CCl4 carbon tetrachloride. So let's start by drawing the Lewis structure. And then we will determine the intermolecular force. I'll abbreviate that IMF. And then we will determine which molecule has a higher boiling point. So if you want to try this on your own first, feel free to pause the video and then we'll go over it together. All right, so let's start with carbon tetrafluoride. So which atom goes in the middle? Carbon. I think you've probably started to notice a theme here. Carbon is usually the central atom. All right, and then fluorine. Let's see, we have 4 fluorines and 4 unpaired electrons. Perfect. And how many valence electrons does fluorine have? 7. So it will have 1 unpaired electron and 3 lone pairs of electrons. And you don't have to draw the dots here that make up the covalent bonds. You can just draw the lines, that's fine. In fact, I might start skipping that step in the future. But we're still reviewing Lewis structures, so we might as well follow that example. Okay, let's draw the Lewis structure for carbon tetrachloride. Which atom would go in the center? Carbon. Okay, and then how many valence electrons does chlorine have? Also 7. Okay, so we've got our 2 Lewis structures. They look very similar, other than the, fluorines and chlorines. Now, let's consider the central carbon atom in each of these structures. What is the steric number of each of those carbons? 2, 3, or 4? 4. There's 4 bonded atoms on each carbon. Okay, so if the steric number is 4, what is the hybridization of each carbon? Is it sp, sp2, or sp3? sp3, great. Okay, so now let's figure out the geometry of each of these molecules. So are they linear, trigonal planar, tetrahedral, trigonal, pyramidal, bent. They're tetrahedral, right? So I'm just going to write that down below each. So they're both tetrahedral. We also said that both central carbons are sp3 hybridized. Okay, let's also consider dipole moments. Do either of these molecules have a net dipole moment? And when I ask that question, I'm not really asking about the individual bonds. I'm asking about the whole molecule. No, so even though we might have individual polar bonds on each molecule, remember that these are tetrahedral molecules. So all of these bonds are 109.5 degrees apart. And it's like that game of tug of war again. Everyone's pulling in equally spaced directions, so nobody wins. So both of these molecules do not have a net dipole. Okay, so without a dipole moment, what force does CF4 experience? Does it experience London dispersion, dipole-dipole, hydrogen bonding, or ionic forces? Well, without a net dipole moment, it will only experience London dispersion forces. So that's what's really interesting about this molecule is even though the individual bonds are polar, overall the molecule is not polar. So it only experiences London dispersion forces. Now what about CCl4? What type of force does that molecule experience? Also London dispersion. Again, we don't have a net dipole or any hydrogens, so this is London dispersion. Okay, so these two molecules again are super, super similar. So how do we figure out which one has a higher boiling point? Well, remember from earlier, we said that a greater surface area equals a greater boiling point. Okay, so now we've narrowed it down to fluorine versus chlorine, right? Those are the only differences here. So which atom is bigger, fluorine or chlorine? Chlorine is bigger than fluorine. So it might be worthwhile to go back and kind of go over some of those periodic trends like atomic size, ionization energy, etc. All right, so if chlorine is larger than fluorine, then which molecule would have the greater surface area? CCl4. And I'm just going to abbreviate surface area as SA, but feel free to write out the full words if you can't remember that. I'm terrible at abbreviations and acronyms, so I totally understand writing things out. Okay, so now let's figure out which molecule has the greater boiling point. CCl4, because it has a greater surface area. All right, so let's actually write down the boiling points of each. So the boiling point of CF4 is negative 128 degrees Celsius. And then the boiling point of CCl4 is 77 degrees Celsius. That is a huge difference. And it's all because of the fact that chlorine is bigger than fluorine. So even though both molecules only experience London dispersion forces, which are pretty weak, that surface area has a huge effect on the boiling point. So these are some things that we'll think about going forward in organic chemistry. We'll often compare molecules and make some predictions about them, just based on properties like size. Okay, so now let's also compare the molecules formaldehyde and methanol. Now, just a little bit of background on these two. You might already know that formaldehyde is used to preserve tissue. If you've ever smelled formaldehyde, it's awful. I don't recommend it. In fact, formaldehyde can cause cancer, so it's a carcinogen. So carcinogenic is just a fancy word for it can cause cancer. And in fact, scientists have been trying to find alternative preservatives to use because, for instance, in morgues, they often use formaldehyde, but with prolonged exposure, that can be obviously deadly. So we're trying to find some different chemicals to use there. Methanol is also called wood alcohol. And this alcohol is what bootleggers sometimes use in place of ethanol. However, methanol is really dangerous. Methanol can cause blindness if you drink too much of it, or if you're exposed to it in any high amount. The typical alcohol that people drink is called ethanol. So ethanol has 2 carbons and a few more hydrogens than methanol, and that makes all the difference, which is kind of interesting. Okay, so let's draw the Lewis structures for these two. So in formaldehyde, carbon again is in the center. And then we have 2 hydrogens and then a double bond to oxygen. So this is kind of similar to the molecule we drew earlier. And then methanol, we've already seen the Lewis structure, but I am going to kind of draw the geometry out as well. Let's see, so we have something like this. We've got CH3, and then oxygen and hydrogen with some lone pairs on oxygen. All right, so let's compare these two. So on the left, we have formaldehyde, which it looks like has a trigonal planar geometry. On the right, we have a bigger molecule, so it looks like the carbon is tetrahedral, the oxygen is bent. So they're different already in that sense. Now let's consider dipole moments. Does formaldehyde have a dipole moment? Yes. Remember, oxygen is very electronegative, so it will attract electrons toward itself more so than the other atoms in the molecule. What about methanol? Yes. So again, we have oxygen, which is very electronegative. And we would find that the dipole moment kind of moves up towards the lone pairs of electrons. All right. So now let's consider formaldehyde on its own. And pretend you have multiple formaldehyde molecules floating around a beaker. What type of intermolecular forces would those formaldehyde molecules experience? Would they have London dispersion forces, dipole-dipole forces, hydrogen bonding, or ionic forces? So we did say that every molecule has London dispersion forces, right? So what would be the strongest force that formaldehyde would experience? So we can rule out ionic bonding, right? We don't have any full charges on this molecule. And we can also rule out hydrogen bonding because we don't have a hydrogen bonded to that oxygen. So this would only, or I guess the strongest force that this would experience is a dipole-dipole force. What about methanol? What's the strongest force that methanol would experience? Hydrogen bonding. We do have a hydrogen bonded to oxygen. Oh, so this would be H bonding. Okay, so now let's consider boiling points. Which molecule do you expect to have the higher boiling point? Methanol, right? Because it experiences a stronger intermolecular force with other methanol molecules. So hydrogen bonding is stronger, so it's going to take more energy to break apart those hydrogen bonds compared to formaldehyde. So methanol has the higher boiling point just due to the intermolecular force. Okay, one last thing we're going to cover, and then this will be the end of chapter 1. Solubility rules. So you might recall from general chemistry that like dissolves like. So solvents tend to dissolve solutes that have the same or similar intermolecular forces. So, for example, polar solvents dissolve polar solutes, and similarly, nonpolar solvents dissolve nonpolar solutes. Now, a very particular example is oil and water. So oil is composed of a number of carbons and a number of hydrogens. Those can vary depending on the type of oil. But we already saw that carbon-hydrogen bonds are nonpolar covalent bonds. So oil only experiences London dispersion forces. But we saw that water has hydrogen bonding. Now, because of these differences in intermolecular forces, where oil is nonpolar and experiences London dispersion forces, water is polar and experiences hydrogen bonding, these two do not mix. Now, occasionally you'll have, for instance, an ionic compound and water. And ionic compounds are similar to hydrogen bonding in force. So ionic compounds will dissolve in water. And then polar covalent compounds that don't experience hydrogen bonding but do experience dipole-dipole forces will also dissolve in water. So let's talk about a special case, emulsifiers. Emulsifiers can dissolve a wide array of compounds because they tend to be both polar and nonpolar. Or another word for that is amphiphilic. One example is soap. So soap has the general formula, which I'll draw here. So on one end of a soap molecule or an emulsifier molecule, there is a carbon bonded to two oxygens. And we already said that those are polar bonds, right? So we do have a net dipole on that end of the molecule, and that would be considered the polar end of the molecule. But then on the other end of the molecule, we have a bunch of carbons and hydrogens. It just depends on the emulsifier or the soap, how many carbons and hydrogens we have. That's why I put a little X down below. But we already said that carbon-hydrogen bonds are nonpolar, and of course carbon-carbon bonds are also nonpolar. So that end of the molecule is nonpolar. So the polar end of the molecule is what we say, or also known as hydrophilic. Getting tongue-tied. So the polar end of this molecule is attracted to water, or it's hydrophilic. The nonpolar end of this molecule is hydrophobic, or we could say that it's afraid of water. So emulsifiers are really useful if you're trying to remove dirt or oil from something. So let's say we have an oil droplet, and remember oil is nonpolar. The nonpolar end of this emulsifier will be attracted to the oil, and then the hydrophilic part or polar part of this molecule will be attracted to any surrounding, let's say, water. And then what ends up happening is we get a bunch of these that kind of encase, encase this oil droplet and separate it from water, or that could also be dirt on your hand and the soap is surrounding it, and then the water kind of washes it away. So again, emulsifiers are a special case where you have both polar and nonpolar sections of the same compound. Now, in previous years, we have seen many oil spills, unfortunately, and I think the most recent one has been outside of Africa, outside of the island of Mauritius. And one way that oil companies will remove oil from water is with something called a dispersant. So a dispersant basically will trap these oil particles and then kind of weigh them down, so they'll sort of sink to the bottom of whatever body of water they're in. So you can see here we've got a blow up of a surfactant-coated oil droplet. And you can see the kind of the same picture I drew earlier there. Now, unfortunately, a lot of dispersants are toxic to wildlife and to marine life. In fact, down below you can see a picture of the BP oil spill from a decade ago, basically. And initially, BP was using these dispersants and other methods to remove the oil or try to prevent the oil from getting to the beaches and wildlife on those beaches. However, again, these dispersants were toxic to marine life in the water itself. So not a great use of the dispersants, but at least it was preventing some harm to wildlife on land. So, you know, there's always the good and the bad with these different chemicals. But same idea as our emulsifiers here. They were trying to use this idea of an emulsifier to help remove oil. So that's just a real-world example. Hopefully we have better methods coming in the future. Um, or, we could just move away from oil, but I guess that's my personal opinion. Okay, so that wraps up chapter 1. And in chapter 2, let's see, let me flip to chapter 2 here in my textbook, which of course is right in front of me. So in chapter 2, we're going to discuss molecular representations. So how do we draw organic compounds? We'll also talk about how to identify lone pairs, how to draw three-dimensional structures. We'll also get into something called a resonance structure, which you might have gone over in Gen Chem, but if you haven't, it's okay. We'll go over it again. So we're going to really start diving into the basics of organic chemistry. Now, again, if you have any questions, you can always schedule an office hour with me on calendly.com/kdavidsonTCC, or you can email me. We can set it up that way too. You can also attend my office hours during the week, or you can post your questions to the Chapter 1 discussion board. So good luck, and I will see you all in Chapter 2.